In a few previous videos, I covered the essentials of variance and type rejections in Kotlin. And today I wanted to make one more video that draws together a lot of those concepts from those videos. There are really just three simple rules that determine when one type is a valid subtype of another type. And if you understand those three rules, you can pretty much reason your way through any subtyping, whether it's generic or otherwise. So what we're going to do today is we're going to look at those three rules, and then after that, we're going to see how they apply to regular type inheritance, declaration site variance, and use site variance. So let's jump in. Let's say we've got two different types, and we want one to be a subtype of another. Well, in order for one to be a subtype of the other, we have to be able to substitute it for the original. And so the question that we're asking today is what things need to be true in order for it to be a valid substitution. And by the way, these three rules apply to both functions and properties, but for simplicity, we're just going to focus on functions today. So here are the three rules. First, the subtype must have each of the non-private functions that exist in its supertype. And this rule is quite intuitive. If a subtype doesn't support one of the operations that a supertype has, then obviously it wouldn't be a suitable substitution because you wouldn't be able to call that operation on the subtype. And second, the function parameter types in the subtype must be the same as or more general than the corresponding parameter types in its supertype. And this one's known as the principle of contravariance. And third, the function return types in the subtype must be the same as or more specific than the corresponding return types in its supertype. And this one is the principle of covariance. For rules number 2 and 3, we saw those in action in a previous video. So if you're not sure why these are rules, check out that video for more background. Now in this video, I'm focused on how these three rules apply to types. But I did want to mention that they also apply more broadly to things like behavior and state. So for example, rule number 2 would apply to all preconditions of an operation, and rule number 3 would apply to all postconditions of an operation. If you're interested in those kinds of things, you might want to pick up this book, which is Fundamentals of Object-Oriented Design in UML. It's a bit of an old book at this point, but I've read it a good 2 or 3 times over the past 15 years, and it's a great read. So again, for today, we're going to focus on the types. So let's get started by looking at regular old class inheritance and seeing how these three rules come into play. Let's use the same models that we've been using. We'll have a vending machine along with a hierarchy of product, snack, and candy bar. The vending machine in this code that you see here returns a random snack, and the candy bar machine returns a candy bar every time. Now, all three of these rules are naturally true when we use regular old class inheritance in Kotlin. So let's look at them one at a time. First, we've got the rule of same operations, and that was that a subtype must have all of the non-private functions that exist in its supertype. So how does this apply to regular class inheritance? Well, a subclass automatically inherits all of the non-private functions from the superclass, so this rule is satisfied. Second is the rule of contravariance, where the function parameter types must be the same as or more general than the corresponding parameter types in the supertype. And indeed, all of the parameter types are the same as they were in the superclass. So rule number 2 is good. Number 3, the rule of covariance, where the function return types must be the same as or more specific than the corresponding return types in the supertype. And by default, all of the return types are also the same as they were in the superclass. Although, as we saw in an earlier video, we can actually declare a function to have a more specific return type in the subclass. So there you go. All three of these rules are satisfied very naturally when using regular class inheritance in Kotlin. Now, these same three rules apply when we're dealing with generics. And in fact, we use variance modifiers to ensure that we're following these rules. I'll show you what I mean. Let's start with the out modifier. Here's a generic version of our vending machine. As it is, a vending machine candy bar would not be a subtype of vending machine snack. One way to make this happen, though, is to add a variance modifier to the type parameter. If we add the out modifier to t, we'll get the subtyping that we wanted, but then the refund function is going to cause a compiler error because we just promised Kotlin that t would only be used in the out position and refund is using it in the in position here. So I'm just going to comment out this function for now. Let's use our three rules of subtyping again and see whether vending machine candy bar follows the three rules required in order for it to be a subtype of vending machine snack. Rule number 1, same operations. Because the base generic type is the same between these two parameterized types, they both have the same non-private functions. So rule number 1 is satisfied. Rule number 2, contravariance. They also have the same parameter types, so rule number 2 is good. Rule number 3, covariance. Now, in order to satisfy rule number 3, we just need to make sure that the return type here is the same as or more specific than the type here. And if not, then it's not going to be a subtype. But if so, then it is. In this case, candy bar is indeed the same as or more specific than snack. So rule number 3 is also good. So all 3 rules are satisfied, and vending machine candy bar can safely be a subtype of vending machine snack. Now, the same thing applies to the in modifier, of course, but let's take our time and, just to be thorough, watch it play out. By switching this from out to in, the compiler is now fine with the refund function, but purchase becomes a problem. So like last time, I'll just comment out the offending function for now. And now let's look at the effective parameterized types for vending machine snack and vending machine product and check the 3 rules. Rule number 1, same operations. Just as before, because the generic type is the same between these two parameterized types, they both have the same non-private functions. So rule number 1 is a given. What about rule number 2, contravariance? Since the type parameter shows up in the in position, we have to ensure that the parameter type here is the same as or more general than in the supertype here. If so, the rule is satisfied, and if not, then this won't be a subtype. For rule number 3, covariance, we can see that the types are the same here and here, so the rule is satisfied. So for declaration site variance, we can see these 3 rules are in play. Now remember that these 3 rules only tell us whether it's logically safe for one type to be a subtype of another. It doesn't tell us whether Kotlin's actually going to regard one as a subtype of the other. And in fact, in Kotlin, if you don't use in or out, the compiler is not going to understand your intent, and it's not going to treat one as a subtype of the other, even if they technically, logically could be a subtype. Okay, here's the same class, but without any variance modifier on it. As we saw when we added the in or out modifiers to t, we had to remove one of the 2 functions. But if we wanted to keep both functions, we're going to have to use useSite variance instead of declaration site variance. And by putting a variance modifier on a type argument instead of a type parameter, we can create a type projection. And type projections are designed to satisfy these 3 subtyping rules. So let's see how that works. As we covered in an earlier video, when we create an in projection, Kotlin changes all of the return types where the type parameter appeared, and we end up with types that look like this. Let's consider the same 3 rules again. First, we've got the rule of same operations. And same as always, since the base generic type is the same between these 2, we have the same non-private functions, so rule number 1 is satisfied. Rule number 2, contravariance. The parameter types in the purchase function are the same, so those are good. And the parameter types in the refund function are simply determined by the type argument. So as long as this is the same as or more general than this, then the rule is satisfied. And if not, then this won't be able to be a subtype. In this example, they are. And third, the rule of covariance. The return types for the refund function are the same, so we're good there. But now comes the interesting part. In the purchase function, we've got the type parameter used in the out position. Is this the same as or more specific than the one here? Well, if the type were just the type argument, then the answer would be no. So this would not be safe as a subtype. And this is the reason that when we create an in projection, Kotlin replaces the result type with a nullable any. And now we can ask ourselves again, is the type here the same as or more specific than the one here? And it sure is. In fact, it'll always be the case. Since nullable any is the supertype of every type in Kotlin, then no matter what the type argument is here, it'll definitely be the same as or more specific than a nullable any. So by changing the return type, Kotlin satisfied rule number 3 for us. Now this works for out projections too. Rule number 1, same operations, and same as always, since the base generic type is the same between these 2, we have the same non-private functions, so rule number 1 is good. Rule number 2, contravariance. The parameter types for the purchase function are the same, so we're good there. But what about the refund function? Is this parameter type the same as or more general than the one here? If the type here were just the type argument, then the answer would be no. And this is why, when we create an out projection, Kotlin looks for all the places where the type parameter shows up in an in position and replaces them with a type called nothing. And with that change, we can ask ourselves again, is the type here the same as or more general than the one here? Yes, and the answer will always be yes, because nothing is the subtype of every type in Kotlin. The type argument here will always be the same as or more general than nothing. And then rule number 3, covariance. The return types of the refund function are the same, so that's good. And then as for the purchase function, the return types are simply determined by the type argument. So as long as this is the same as or more specific than this, then the rule is satisfied. If not, this won't be a subtype. So by changing the parameter type of the refund function, Kotlin satisfied rule number 2 for us, which gave us the subtyping that we wanted. And finally, let's see how star projections satisfy these 3 rules. Rule number 1, same operations. And same as always, since the base generic type is the same between these two, we have the same non-private functions, so rule number 1 is satisfied. Rule number 2, contravariance. In the purchase function, the parameter type will always be coin, so that's fine. What about the refund function? This type has got to be the same as or more general than the type here. As with the out projection, Kotlin simply uses the nothing type, so that any type here will always be the same as or more general than nothing. And finally, the rule of covariance. In the refund function, the return types will always be coin, so that'll always be the same as, that's fine. For the purchase function though, the return type uses the type parameter. And so this type has got to be the same as or more specific than the type over here. And similarly, Kotlin uses the nullable any type here. That way, no matter what the type argument is over here, it'll always be the same as or more specific than a nullable any. And because Kotlin is using the uppermost and lowermost types in these positions, the same 3 rules hold true for any other parameterized types created from the vending machine generic. So this works for vending machine snack, and also for vending machine candy bar. And no matter what that type argument is, all 3 rules will be satisfied. And there you go, with just 3 simple rules, you can reason your way to understanding how subtyping is working for generics, whether you're using declaration site variants or use site variants, or regular old inheritance. Don't forget, Kotlin and Illustrated Guide Chapter 19 covers these concepts in detail, with one concept building upon another. And so if you're still struggling with it a little bit, that's okay. Just go check out that chapter. I'll include a link in the description below. Also, be sure to sign up for my brand new email newsletter. I'm excited about that. Be among the first to know about any new articles or videos or other projects that I've got up my sleeve. You can do that at newsletter.typealias.com. As always, feel free to reach out to me in the comments section below or on social media with any thoughts, ideas, or questions that you have. I will see you next time.
You've read the chapters online, and now I'm proud to present the Lean Puff edition of Kotlin and Illustrated Guide. Take the book offline with you, mark it up in your favorite PDF software, and get early access to new chapters as they're written. You can pick up your copy today. Just go to book.typealias.com.